Yes, definitely. That's what I always forget to do. So basically we came up here with the result that if I set R equal to, is a little bit of algebra, 2 square root of L over C, then I am at critical damping. And again, this is for a series circuit. Okay, you get to do this in the lab. And so I'm going to give you a little bit of advice here. Okay, so I've got something that looks like this. V1 is going from 5 to 20 volts. So V1 is going to have an equation that looks like it's 5 at t equals 0 plus 15, so that the final answer adds up to be 20. E, boy, okay, sorry. 15 e to the minus t over tau. So there's an equation for V1 of t. If I want to measure tau, I could say, okay, what is V1 at time t equals tau? At time t equals tau, tau over tau is 1. So it will be the answer to whatever 5 plus 15 e to the minus 1 is. I can plug that into my calculator and come up with 10.5 volts. So if I want to find the time constant, I find the expected value at one time constant, which is 10.5 volts, and then I'm just going to go over here, and you can do this with cursors in multisim. I look for the place where the red curve equals 10.5 volts, and I look down, and I see the time constant is approximately 1 second. And you can measure those with cursors and multisim, and I believe you get to do that in lab 1. It's great, just even being there, like today in lab. I wasn't really in lab, I wasn't involved with it, I was doing other stuff, but just hearing it in the background is enough to remind me. I wrote the lab, so is enough to remind me of where you're at and what you're doing.
Do you mind going back for a quick second?
Sure.
Okay, thank you.
Okay, so if I look at this S1 and S2, for a series circuit, they're always the same. There's always this R over 2L. It appears several times in the equation. So what I'm going to do is replace R over 2L with alpha. And 1 over LC shows up a lot. And I'm going to replace 1 over LC with omega naught squared. So this thing called omega naught actually equals 1 over root LC. I will tell you at this point in time, if you ever have to guess what omega naught is, just say 1 over root LC and you're 100% guaranteed to be right, unless they did something really weird. Right. So if I can go through, look at my series circuit, if I know R and L, I can calculate alpha. And alpha's in this funny units called nepers per second. Let me just get this out of the way. And omega naught, if I know L and C, I can calculate omega naught. And omega naught is in a more familiar unit called radians per second. This, whatever I saw nepers when I was a sophomore, I would start to break out in a sweat. I would ask people, what's the difference between a neper and a radian? And I could never get a straight answer. And as far as I could tell by going through the equations and the solutions in the book, and I had to do this the first time I taught this class, there is no difference between a neper and a radian. I am to the point, whether you, when I ask you to calculate alpha or omega naught on a test, If you write down nepers per second or radians per second, I don't care. I'm going to give you credit for it either way. And when the craziest thing about it is when you calculate alpha, and let's say it comes up to be 4, and you calculate omega naught and it comes up to 2. You're going to ask yourself, is alpha, what's the comparison between alpha and omega naught? In this case, alpha is greater than omega naught. 4 is bigger than 2. And just forget about the units.
I'm a little confused on why you square rooted LC.
Because this is omega naught squared here, and this is just 1 over LC. So if you're solving for omega naught by itself, you got to take the square root.
Thank you.
Okay. So in this case, alpha was greater than omega naught. You would have, oh, great. Oh, you had to do it this way. This is repeated real roots. If alpha equals omega naught, you have repeated real roots, and this is critical damping. Starting to see the pattern here. If you have complex conjugate roots, omega naught is bigger than alpha. Good, I lined these up. I fixed some of these. Omega naught is bigger than alpha. You have underdamping. If you have negative real roots, you have overdamping. Alpha's bigger, yes. You have overdamping. The person who originally wrote these slides made these all multiple choice problems, where you had matching problems. I put them all in order because it's easier to talk about. Okay, so just by calculating alpha and omega naught, knowing the R's, L's, and C's for a series circuit, you can figure out what type of damping you have. And you pretty much know whether you're on the right track for the type of system you want. Okay. Once I know the type of damping.
Back right quick, sorry.
Yes. Yeah, no, please. Good. Somebody's at least awake.
Okay, you're good.
Okay. Once I know the type of damping, and I can figure out the type of damping just by calculating alpha and omega naught, I know the form of the solution. If it is overdamped, it's going to look like the sum of two exponentials. We've already figured out how to calculate alpha, omega naught, S1 and S2. So for this one, the only things that are left to get the solution are A1 and A2. For critical damping, if it's critically damped, this form of the solution looks like this. We know alpha. T, it's a function of T, so I can leave it in there. Again, I just need A1 and A2. And the same thing here. The only variables left, oh, I don't know what omega D is. We'll get to omega D a little bit later. Omega D is just, I can calculate from alpha and omega naught, but we need to find A1, A2, and omega D. If I can find those three things, I could have the solution. Now, one thing that tends to trip people up is in this case, these are written as I as a function of time. Remember, these are differential equations. If I'm solving for voltage, the form of the solution would look the same. If I was solving for power, the form of the solution looks the same. What would change would be the constants A1 and A2. If I was doing a mass spring system, and that's why mechanical engineers take 325, and I throw those in there occasionally, and I was measuring the force, I could do the same thing and make it force as a unit of time. What would change would be the units of A1 and A2 and how I calculated them from the initial conditions.
Can you
Okay,
repeat that one more time?
so the only thing that would change if I was solving for a different variable would be the units of A1 and A2 and the way I would calculate them from the initial conditions. And we'll go through that process a little bit later in the class if we get that far. Okay. All right, so this is what we've learned so far. This is key slide number 1. For a series circuit, we have to first of all look at our circuit and decide if it's series or parallel. Once we do that, if it's series, this is the equation for alpha, and the equation for omega naught doesn't change. If it's parallel, I'm not going to derive this, but you can do it for fun or read the Nilsson book. What's going to happen is alpha equals 1 over 2RC for a parallel circuit, but omega naught stays the same. So the first thing I do is I determine if it's series or parallel, calculate alpha and omega naught, and that will be the first step on all of these, and we'll get this into a multi-step process soon. And once I know the type, and once I compare alpha and omega naught, I can figure out what the form of the solution looks like. And whether it's a current or a voltage, it's going to have the same form. If it's overdamped, I'm going to need S1 and S2. I can calculate them from this formula. And if it is underdamped, the additional piece of information I need is omega D, and I can calculate that using this formula. So a lot of information on the sheet. You've got to practice the problems to learn how to do it. There are a lot of example problems being worked out in the audio review notes of 280. I've got a series and parallel, both underdamped, overdamped, and critically damped, 6 different combinations worked out in detail. And I will do some of those in the slide sets. I won't have enough time to do all of them.
What exactly is the response on that table? Is that like a graph of the curve of the line, or?
Yes, so if you're solving for current, it's an equation that you could use to plot the current as a function of time.
Okay.
Yeah, good.
Thank you.
You guys are more alive than the kids have been the past couple of years. I don't know. I mean, maybe it's because I'm more awake. That might be helpful too. Because I don't have 4 classes before this. Now, to determine my 2 unknowns, A1 and A2, I'm going to need 2 equations. 2 unknowns, 2 equations. Assuming we can go back to that other slide and calculate S1 and S2. So this is how you get the 2 equations. I'm going to plug in t equals 0 into each one of these equations. This is we have so one or the other. So I plug in t equals 0. I'm going to get I of 0 is A1, e to the 0th is 1, plus A2 times e to the 0th is 1. Yay. So this is I of 0. In the next situation, this is, let me look. That's critically damped. Okay, so this is my overdamped, critically damped, and that's definitely underdamped because it's got cosines in it. If I plug in I of 0 in case B for critically damped, I get A1 e to the minus 0 is 1 plus A2 t e to the minus 0 equals whatever the I of 0 is. And in the third case, e to the minus at is always, I'm plugging in for I of 0. This is 1, so it's just multiplied. I get A1, the cosine of 0 is 1, and the sine of 0 is 0, so A2 goes away, equals I of 0. So if I know the initial condition on the voltage or the current or the power that I'm solving for, I get one equation. One of them gives me A1 directly. The other two gives me things that I have to, oh, T would be 0, wouldn't it? T would be 0, so this goes away. Sorry, A1. So I've got one of the equations I need. I still need an equation to solve for A2 and B and C, and I need a second equation for A. Now what I'm going to do here is I want to take, well, let me answer the question down at the bottom and then I'll get to my next point. The derivative of E1 to the ST with respect to T. I want to take the derivative of an exponential. Remember, it's the derivative of what the exponential is raised to. So with respect to time, so it would be S1 E to the S1T. Okay, we're going to use that. My second equation, this involves calculus. We want to find the derivative of these three equations. I'm going to do the first one, and the rest of them are in BB Learn. If I take the derivative of this equation, I prime, what I get is A1 S1 E to the ST, S1T, pretend you get plus A2 S2 E to the S2T. Now, that's the derivative here. If, okay, where am I going with this? If I evaluate the I prime equation, what I want to do is I want to evaluate I prime at 0. So this is I prime right here. If I evaluate I prime at 0, I get A1 S1 plus A2 S2. And we can go through it, we can do the calculus, we could take the derivative of this, evaluate it at 0, we could take the derivative of this, evaluate it at 0, but there's the answer. So if I know, for part A, if I know the derivative of the initial condition, if I can find the rate of change of the current at time t equals 0, I now got another equation from the last one. I of 0 for that particular case was A1 plus A2. We've got formulas for S1 and S2. If I can figure out these, like they're like boundary conditions, initial conditions is what they call them in math. I've got two equations and I've got two unknowns, and I can solve for A1 and A2. Okay, we've got the theory. We've gone through this one before. I've got the circuit. I determine if it's in series or parallel. I calculate alpha using one of two equations. You know the sound. Okay, I will be back. We're on slide 18.